In this video, we'll talk about conic sections. Conic sections are, or conics as an abbreviation, are a result of intersecting of a cone, three-dimensional cone as a plane. This talks about, in this section, we'll talk about a little bit about 3D geometry or just classic graphs within math, like circles, ellipses, parabolas, and hyperbolas. Ellipses are circles that have has a longer radius on one side. So a circle, which usually is like a squared plus b squared is equal to 1. An ellipse would have like 2a squared plus b squared is equal to 1 or something like that, where one of those side radiuses is not the same and it actually is longer. Parabolas are ellipses that don't have an end to them. So if this is a circle and this is an ellipse, which is just a giant oval, then a parabola is just like an ellipse with no end to it. It just kind of looks like that, but it never comes back around either. It always is growing outward. Even if it's slow, it's still going outward and getting bigger. Hyperbolas are a little bit harder to draw. There's like some asymptotes involved here, but basically they would look like that. Anyway, so let's move forward and take a look at what conic sections are, how they relate to these graphs. So as I said, a conic section is when you're taking like a planar slice of a cone. The way that these graphs relate to the conic section, you can kind of see through these pictures. A circle is given when you take a planar slice directly even and perpendicular through the cone, like so. If you come at the cone at a bit of an angle, then now suddenly this is not a perfect circle and it's elongated on one end, giving us an ellipse. If you don't go through the full cone and just go in on one side as such here, we'll get a parabola. And if you go through both the top and bottom cone, then we get a hyperbola. This is what I was saying. It's kind of like hard to draw. Like the edges of the cone here are synonymous with like an asymptote, and then the hyperbola is the thing on the outside of it. So how are these geometries important? Parabolas are used for satellite dishes and telescopes. I can tell you that firsthand since I'm an astronomer dude. They're very important when designing these telescopes and getting the angles right for the dishes. Ellipses are good for modeling orbits of planets because, as you know, most of our planets don't orbit the sun at a circular orbit. Almost all of them have some type of elliptical pattern that they're orbiting around. And this actually, I didn't know, but it's cool that hyperbolas are used when modeling to locate lightning strikes and nuclear cooling towers, or in help in designing nuclear cooling towers. Going in depthly into each one, first we have the parabola, which I think is probably the most used and most important of these designs and geometries. The parabola has some distinct key features. The parabola is a set of all points, so it consists of all real numbers unless the domain is specified. There is a vertex at the very bottom of this parabola, which denotes exactly where the slope is exactly 0 for a split second. And then as soon as it becomes, right off of the vertex, then it becomes positive slopes or negative slopes, depending. But there's only one place on the parabola where the slope is exactly 0 and horizontal like that, and that's where the vertex is. The other two key things for parabola are the focus and the directrix. The focus and directrix are equidistant from the vertex, meaning like, as you can see here, like these distances from the parabola to the focus or the directrix are exactly the same. The directrix is the axis of symmetry perpendicular across this direction. The focus is hold on. So the directrix is actually perpendicular here to the axis of symmetry, whereas the focus and the vertex lie on the axis of symmetry across the y-axis, where like this can fold over and these have exactly the same y values, just at different x values. Other than that, just remember that the parabola is always growing, so it really is between negative infinity and infinity, because these arrows don't stop and they keep going. So whenever you're asked about the domain and range, you would say the domain is from negative infinity to infinity, and the range is whatever this y value is to infinity. In this slide, you can see how to relate the parabola graph to the parabola equation. If the parabola is translated h units horizontally and k units vertically, the vertex will be at the point h, comma k. And as the slide says, this translation results into a standard form of the equation when you replace x by x minus k and y by y minus k, where k is, again, this like a distance to the vertex, or like the translation. So right here we have the horizontal directrix with a vertex at hk, and this is the vertical directrix with a vertex at hk. Horizontal because this is in terms for y, and then vertical because this is in terms for x. I know that sounds backwards, but if you think about it, that actually makes sense. Because the vertical directrix would have point along the x coordinate. Good to familiarize yourself with these equations and how the translation of adding h or k relates or like falls into the equation for a parabola here at x and y. So continuing on, we can talk about the properties of a parabola again. Axis of symmetry at the point of the vertex or the focus, which is at hk. Wait, the vertex or the focus? Let me make sure I get the right. The vertex, yeah. Okay. Talking about the properties again, this is the axis of symmetry is at the vertex on the point h comma k. The equations for the horizontal or vertical parabola look like this, with the focus being at h plus pk for the horizontal, or hk plus p for the vertical. The directrix here is for the horizontal h minus p, and for the vertical k minus p. And then the endpoints are from the focal diameter are this. These aren't quite as used as much, I don't think. So it's really understanding the axis of symmetry, the equation, and the focus that are really the money makers for understanding parabolas. The whole goal here of it is to eventually learn how to draw parabolas given a limited amount of information. So in the first example, we're tasked to find the equation of a parabola described by what they give us and create a sketch. So if they give us the focus, the directrix of the line y equals -3, in the form of the parabola given by x squared is equal to 4 times ay. This is like the general form here. A here would be equal to 3 because that's from the focus. Y and x are just part of the equation. So really this is x squared is equal to 12y is our equation for the parabola. So if we were trying to find what is it supposed to say? Example 1. Okay. So if we were to change this example to where it's not having a vertex at 0, 0, but now has a vertex that's somewhere along the graph, like translated somewhere, they tell us that the focus here is now at -1, -2. Directrix is y equals 3. This is the general form of the equation for a parabola that you would use, recalling which is h and which is k. So after being able to identify what your h and k is, then it's a matter of plugging it into your equation for the parabola. They give us the equation for the focus, which if you recall, the focus isn't exactly 1-to-1 as like the vertex is. So the focus over here tells us that h is the first value and the second value is actually k plus p, or h plus p and k, depending on if it's horizontal or if it's a vertical parabola, which it is a vertical parabola. So we're going to use the one where k is, it's h, k plus p, because we're working on a vertical parabola. So with that being said, h is just equal to -1. So plugging that in, I'd have x minus a -1. So I get x plus 1 now. For k, now that I'm doing k plus p, I get k is now equal to 1/2. Well, this thing right here is k plus p.